Hello everyone, welcome back to the channel. It's been a little while since I put out a video. Been busy with personal life and working on some projects, but I've started my new project now and I thought I'd get this out to you guys and show you what I've figured out. So the main reason why I'm doing this part of the video is because when I went to looking around on the internet and whatnot, I couldn't find a whole lot of information that was useful to me about programming this chip. And so I thought I'd make a video to show you what I've figured out. The board I'm using here, the chip I'm using for my next project is this AD9834. It's an analog devices chip. It's a direct digital synthesis, and it's a 75 megahertz DDS chip. You can read all about the information for this part here. The information is available online, any of your electronic parts retailers. And there's a lot of really good information in the data sheet. But what I've done is I've got a couple of these demo boards, and I got these on eBay. This one I don't remember the seller's name, but he was the only seller that was selling these out of the continental U.S., somewhere over in California. So I picked up two of these boards. I think they were $18 a piece, and that's shipping included. And they got here pretty quick, about 4 days, over to the East Coast. And I've gone online. There are some libraries out there. I use when I do programming. I'm not an avid programmer, so I use Arduino because it's pretty easy to pick up and learn, and that's what I've used, and that's what I'll be using for controlling this chip. But like I said, there are some Arduino libraries out there for the AD9834, but I kind of wanted to not use those libraries so that I could sort of tailor this code to work in my project, and that's what I've done. And then I'll show you the code and what I've some of the basics to operating this chip here in a minute. I realized, from my last video when I did the work on the Heathkit AR15, part of the alignment process for that receiver was adjusting the stereo multiplexer circuits, and I realized, I don't have a stereo composite generator, and so that's where all this sort of originated from, working on building a stereo composite generator, and I needed a way to generate tones for the 19 and 38 kilohertz tones for making a stereo composite signal. I actually have two of these boards. I've got this one plugged up here onto a breadboard, and it's wired into our Arduino Nano board. And this is just sort of like a test setup here. This won't be the final product. I've got my other more complete circuit on another breadboard. We'll look at that later on and see how that works. But it's pretty easy to set up. It uses this chip uses the SPI protocol for communications, and I've got this set up here using the SPI, and you can go and learn more about SPI. I'm not going to go into the specifics on SPI, but I'm using the SPI pins here. I've got the F-Sync pin on which is this brown wire here. That's going to a digital pin, and that can be any digital pin you choose. You just set up in your program. And the S-Clock, which is the gray wire, goes to the S-Clock pin on the Arduino board, and then the S-Data pin goes to the MOSI, which is the master out slave in pin on the Nano board. And then I've got 5 volts and ground going back to the board. And this yellow lead here, we'll talk about in a minute, is a hardware reset pin, which is available. The hardware, the reset, and the frequency select and phase select controls are taken out to pins on this on the AD9834, and I've used that because I needed that functionality for this project that I'm working on. And I've got that wired out to another digital pin on the Arduino Nano board. It doesn't really matter. I think it's on D8 on this setup here. But like I said, again, that's also a arbitrary digital pin you can use for whatever you need. I've got the output, one of the outputs here, hooked up through this coax, and that's going over to this oscilloscope right here on channel 4, and as you can see right now we're generating a 19 kilohertz sine wave, and that is what I needed because I'm going to use this to generate the pilot tone for developing the stereo composite signal. All right, taking a look at the computer screen here, I've got some, this is a test sketch I've written just to do some demonstration here on the board. This is my disclaimer. I'm not a avid microcontroller code writer, so some of this code might be sort of primitive. I'm sure there's probably ways to make this more efficient, but this is the setup that's worked for me. And I'm also feel free to leave comments, but please don't ask me to look at your code or debug your code. There are forums out there on the internet for that sort of thing. I'm not interested in doing that, but I'm just here showing you what I've got to work, and maybe you can take some of this and use it for your coding in the future, to sort of help you out, or at least to get you started, and then you can play around from there. That's the best way to learn this, is just to play around with it and see what works and what doesn't. All right, so just looking at this sketch here, we talked about hooking up the SPI, and this is a standard SPI. S clock goes to D13, which is the S clock pin, and these pins all reference for the Arduino Nano board. If you're using a different board, you may have to look at your data sheet to see where these pins are. But anyway, the S clock goes on to D13, and the S data pin goes on to D11, which is the master out slave in pin. I've included the library SPI.h. That just is the SPI library from the Arduino IDE. First thing we got a couple of pins assigned. We've got an LED on pin 6. We've got a reset pin on pin 8. And I've got the F-Sync 1 on pin 9. And I've also got an F-Sync 2 because I'm going to use 2 of these boards. But this F-Sync 2 isn't going to be used in this sketch. All right, next thing we do is we run our setup, set our pin modes. We're going to digital write. We got to set the LED low. That's just going to tell us when the program's complete. It'll light the LED at the end. And we've got a reset pin. We're going to set that high. This is going to go to our hardware reset pin. And we want to set that high initially, so that when we set the control register later on to enable the reset pin, the part will exit in a hardware reset state. And we're going to write our F-Sync pin high, and that's going to set up our communication with the SPI. All right, we'll initialize SPI, set data mode to mode 2. And the reason we set data mode 2 is if you read the data sheet, it talks about the timing for clocking in the data to the AD9834. And what it says is the S clock pin must be high when the F sync pin is taken low. So the F sync is basically the chip select pin, and when that pin is taken low, that tells the device, the AD9834, to get ready to receive a command word. Which basically that's going to initiate the command transfer from the microcontroller. And when the F-Sync pin is taken high, that tells the AD9834 that the command word is complete and to go about doing what it was doing before. All right, the data sheet also talks about bits are clocked in on the falling edge of S clock. And so when we set SPI mode 2, that's going to set up the conditions for the SPI transfer. Set bit order MSB first. And then, all right, so now we've set up our SPI. Now I've got the code to run 3 subroutines here. First we're going to run as an AD reset, then we're going to run an AD frequency, and finally we're going to run an AD enable. And what these do is they're going to address the registers in the AD9834 to set up the chip for the various functions. First thing we're going to do is we're going to do an AD reset. So it's going to send us down here. We're going to run this reset routine. And what this does is this sets up the AD9834 in a reset condition. And this is recommended on the data sheet. It recommends placing the part in reset when you first power it up. And what it does is it resets the internal registers and sets output to mid-scale. It does not change the frequency or phase registers. That data is not affected by the reset command. All right, so as I mentioned before, we're going to set digital to write. We're going to set the F-sync or the chip select pin to low. That will tell the AD9834 to prepare to receive a command. We will transfer out the reset command, which is it's done in it's a 16-bit word, and it's done in the SPI is going to transfer it to 8-byte words. So the first word we're going to transfer is and these are all in hex, is OX21, and then we're going to send a 0. This is a data sheet from Analog Devices. This is application note 1070, and it's basically a application data sheet for the AD9833 and the AD9834, and it's also on the internet, readily available for anyone. You can just put this in your favorite search engine and find it. And it basically just goes through and it tells you sort of how to, like just a generic programming sequence for setting up this chip, and it's kind of just to get you a working example of how to program. But the first thing it does is it calls the reset, which is this OX2100. And if we look at the bits here, so for the AD9834, to address the control register, bits 15 and 16 here are set to 0, and that tells the part to address the control register. Bit 13, there's a most significant bit register and a least significant bit register. And this bit here tells you whether you want to address both registers sequentially or whether you want to address the registers individually. And that's that information here is on the data sheet. And I'm not going to go into a whole lot of detail, and that's data bit 13 right there, DB13, and that explains how that what that bit does. And I'm not going to go into a whole lot of detail, but you can read the data sheet and get that information there. The next, of course, these next bits are all 0, and in this bit here, which is bit number 8, is the reset bit. So our bit 8 right here is the reset bit, and when we set that bit high, reset 1, it's going to reset the internal registers to 0, and that's what we just talked about. So that's the first thing that happens here. We put this word in here, this OX2100. It's going to put this binary string onto, it's going to transfer this into the control register because we're addressing the control register. What I've done is I've basically written the part, I've written the code so that the program runs a reset continuously in the main body of the part, which is, and the reason I've done this is to demonstrate here the SPI word transfer. I guess if that's what you want to call it, but basically the SPI communication transfer from the microcontroller to the AD9834. And the reason I'm doing this is because when I was initially trying to get this part to work, I was having a lot of problems with being able to communicate from the microcontroller to the AD9834, and I found that when I started probing the control or the communication pins, I was able to figure out what my problem was. And my problem was I had the SPI mode set incorrectly in the program. And so that's why I'm showing this here, is to show you what, kind of basically explain how this communication transfer is going from the microcontroller to the AD9834. Because like I said, it helped me, and maybe it'll help somebody out there that's watching this. But I've got, like I said, I've got the code written right now on the microcontroller so that the reset routine is being continually recalled. So it's continuously sending a reset command to the AD9834. And that's what I've got here on the oscilloscope. Now I don't have a logic analyzer or I don't have a logic the logic decode function on this oscilloscope. I'm sure that if you do have a logic decode function on your oscilloscope, that'll make this a whole lot easier, but this is what I've got. So I've got 3 channels. The channel 1, which is the yellow trace, is the F-sync or the chip select pin. The blue trace, which is channel 2, is set to the S clock pin, and the magenta trace here, which is channel 3, is set to the S data pin. So as we can see, and like we just talked about, before the part can receive a command, it has to be the F-sync or the chip select pin needs to be set low, which is what happens here. So the first thing that happens is our chip select pin is set low. Now remember we talked about SPI mode 2, and in the data sheet the clock needs to be high when F-sync is taken low, and so that's what happens here. You see F-sync is taken low, and our blue, which is our S clock, is high after the chip select F-sync pin is taken low. Once that occurs, our data is clocked in on the falling edge, and we have this is our data here. So we see that on each falling edge of S clock we get data, which is the magenta line is clocked in. So on the first falling edge clocked, we're going to clock in a 0. On the second falling edge, we're going to also clock in a 0. On the third falling edge, we're going to clock in a 1. Then we've got our 4th, 5th, 6th, 7th. All our falling edge clocks are all going to clock in 0s, and then on our 8th clock, we're going to clock in a 1. So we're going to go 0, 0, 1, 0s, and then 1 on the final clock. All right, so that's our first 8 bits that were clocked in there. We're going to clock in our second 8 bits. Again, on the falling edge, we're going to clock in a 0, and actually on all of these falling edges. So the second word is 0. So that's what we're clocking in, all 0s on the second word. All right, so there's our 2 8-bit words that are clocked in. And then to complete the communication, the F-sync pin is taken back high, and that completes the communication transfer. So our reset, we want to clock in 0, 0, 1, 0. So we've got 2 0s, a 1, then we've got 4 0s, a 1, and then our second section is all 0s, and that's what we've got here. We're going to clock in our 0, we'll clock in another 0, we're going to clock in a 1, we're going to clock in 4 0s, and we'll clock in a 1. That will complete this first part of the word, and our second part of the word, which is all 0s, we're clocking in there. This is the reset command to the AD9834. So that's what we've done with our code here on our reset. Once we've completed transferring the word, set the F-sync pin back to high to tell the AD9834 that the transmission is complete. All right, once we place the part in reset, next thing we're doing is going to put the part, the AD9834, in to change the frequency register, and that's what this routine here does. This will address the frequency register. The frequency register, it's a 28-bit word. It's sent in 2 14-bit chunks. We're going to send the 14 least significant bits first, and then and that is discussed in the data sheet. It says that the 14 least significant bits are received first when you're talking to the frequency register. Bits 15 and 16 will address the frequency register. We need to set, to address the frequency register, you need to set bits 15 and 16. If you want to go to a frequency register 0, you need to set the bits to 01. And if you want to go to frequency register 1, you got to set them to 10. If you set both of these bits to 0, it will address the control register, which will not change the frequency. So that's one thing I had to learn when I was working on this part. I couldn't figure out why I wasn't changing the frequency register. It's because I wasn't addressing the frequency register with the correct bits. So make sure when you're writing to the frequency register that you set bits 15 and 16 correctly. The rest of your frequency word will be in these other 14 bits. But like I said, you have to break it into, for this setup, we had to break it into 2 words, and they're 14-bit words. The other 2 bits address the frequency register. And I've got, so there's an example right there. So what we're going to do is we're going to initiate, or let the AD9834 know that we want to send a command. We'll set the F-sync pin low. Then we're going to transfer out our frequency word, and the word is OX49A3 and then OX4004. And I'm going to show you now how I got those numbers for the particular frequency. And this word here will sets up the 19 kilohertz frequency for the frequency register. All right, so again, looking at the application note 1070, it tells you how to calculate the frequency register. And what you do is your frequency register word is equal to the desired output frequency times 2 to the 20th power divided by the frequency of your master clock. And this M clock is the clock on the device. So your clock that you're putting into the AD9834, and on these boards it uses a 75 megahertz clock. So you have to use whatever clock is going into your master clock, whichever clock is going into your DDS chip is the frequency that you use for the M clock. And in this example here, they had a 25 megahertz M clock, and we're using a 75 megahertz M clock, so we'll have to change that. This is just a scratch pad here, so algebraically do some manipulation here. But our frequency out that we wanted was 19 kilohertz. We're going to take that, multiply by 2 to the 28th power, and divide it by 75 megahertz. When you get that, we get a frequency word of 68003. And when we convert that to hex, number 0001093, which is this binary number here. And I'm not going to go into the conversion. There's lots of, I just use I use an app to convert numbers from decimal to hex to binary, and you can do that, or you can do it however you choose. But anyway, this is what it converts to right here, this bit string. Now we're only looking at the at 28 bits, so that's going to take us out to here. I believe that's right. So that's we got 4, 8. So that's 1, 2, 3, 4, 5, 6, 7. So that's 28 bits there. So that takes us out to this one. And of course, these are all zeros, so they're not really gonna they're not gonna affect us so much. But we need to break this into two 14-bit words. So we've got 1, 2, 3. So that's 12 bits, and then 14 bits would be here. So that's where we're going to split it. And then we've got 1, 2, 3 right here for our second bit. And then we're going to split it here. So that's our second bit of 14s. And then these zeros, since there's nothing beyond this set here, we can just forget or drop this portion off because it's not going to affect our number. And that's what I've done down here. So I brought the 14 least significant bits down here to this number here and broken it. So there's our 2 zeros, and then addressing our frequency register here with 01. And our most significant bit is the second one, which is these numbers, this bit string here, down here, again addressing the frequency register 01. When you take these numbers here, this first number here, the least significant bit string, and you convert that back to hex, it's going to give you 4983, and the most significant bit string when you convert to hex is going to give you 4004. We can see that we've got our least significant bits, our OX49 and OXA3, And then our most significant bits, we've got 0x40 and 04. So that's going to be our frequency word. The next portion we're going to do is we're going to address the phase register. And for this demonstration, I'm not going to really do anything with the phase register. But the way that's done is the phase register word is it's a 12-bit word. Bits 14, 15, and 16 are used to address the phase register. So for phase register 0, you would start your word with 110. And for phase register 1, you would start your word with 111. B12 in the phase register is a don't care bit. That's just that's information straight out of the data sheet. And then the phase word is the remaining 12 bits, which is right here. I'm going to set this register to a 0 phase adjustment, which is OXC000. And that's what I put here. All right, so we've transferred our frequency word, we've transferred our phase word, and then we're going to complete the transmission by writing the F-sync pin, chip select pin back high to tell the AD9834 that the transmission is complete. All right, once we've set the frequency register, we're going to re-enable the part. And normally, if you don't want to use the hardware reset pin, you would just all you would need to do is write the reset bit to 0, and that would turn the part on. However, in this application, I'm going to do something a little different. When we enable the reset, when we enable the AD9834, we're going to enable it with a hardware reset functionality, meaning we're going to set the pin switch bit high, and that's going to allow us to use the reset pin on the part to control the reset, as opposed to writing to the control register to reset the part. And I'm going to show you how we do that here. So, like I said, we're going to run the AD enable routine, which is down here. And this is, again, it's a control register write. We're going to enable the AD9834 and set pin switch to 1. And this enables the chip pin reset. It's I call a hardware reset. Because we're using, we'll use external hardware to control the reset, not the control register. And we're going to leave the AD9834 in a quote hardware reset state by leaving a high on the reset pin. And the reset pin, when you place a logic high on the reset pin, that places the part in a reset condition. And this is going to be clear at the end of the void setup routine when we enable the, and we're going to enable the pin switch, the hardware pin using the control bit 9. We're going to set that to high. So we'll look at the data sheet and talk about that now. So here is our control register again. We're looking at bit 9, which is the pin switch bit. And that's discussed right down here. Functions that select the phase and frequency registers. So there's pins that will select the frequency register, and there's pins that will select the phase register, and there's pins that will control. There's a pin that controls the reset function of the AD9834, and this is one reason why I chose this part over the AD9833. Because it didn't bring, those functions were not brought out to pins. I think they were only limited to software only. And for my application, I wanted to be able to access those pins externally with hardware. So that's one reason why I chose this chip over the AD9833. But like I said, when we enable the pin switch bit, which is our bit 9 right here, it allows us to control these functions externally. When you set the bit to 1, it implies the functions are being controlled using the appropriate control pins, and that's what we want to do. If we don't want to control them externally, we want to put them on software only, you just set this bit to 0, and then that uses the registers. We looked at that on the data sheet now. Again, so we're going to write our chip select pin, our F-sync pin low. That's going to tell the AD9834 that we're initiating a command. We're going to write our word, which is OX2200. And what this word is going to do is essentially what we just said. It's going to take the part out of reset. So we're going to write the reset bit to 0, which will take the part out of reset, and then we're going to write the pin switch bit to 1, which is going to enable the pins on the AD9834, the control pins for frequency, phase, and reset. And that's what this word does. And then we're going to write the F-sync pin high. That will let the part know that we're done communicating with it. All right, so we've run our routines for reset, frequency, and enable. I've got there's a 2-second delay in here, just a programming delay. And then we're going to take our reset pin low. And what this does is when that pin is set low, it removes the reset state from the device, and it will enable the output. And that's what this digital right here. We're going to take the reset pin low. All right, that completes the setup of the chip. And then the program, of course, will take us down to the main body of the program, which all I've got in here is writing an LED pin high, and that's just to tell me that the program has completed setting up the AD9834. All right, I'm just going to hit the reset on the controller here, and we'll go through the talk about what's happening here. So I've got the reset. I'm going to release the reset. All right, that's our reset there, and now our output here. And we can see that when the part was reset, the first thing it's going to do is go to an output at mid-scale. So we've addressed the control register there, and now the frequency has changed. And now what I'm going to do is I'm just going to change this frequency word here. I'll make this, so we remember our control word for the frequency was hex 49 alpha 3, and then the most significant was hex 4004, and I'll just change that to a 4000, just a 4000. That's going to shift the frequency, should shift it quite a bit because that is changing the most significant bit. We're going to upload that, and we can see, and I don't know what this is going to come out at frequency there. So we see that we've changed the frequency quite a bit. It's down to just under 700 hertz. And we can change that word. I'm going to change it to 4001 on the most significant bit, and we'll reload that. But there we go. So, and it's writing, and so now we've written to, it's a little bit higher now. So it's like a 5.2 kilohertz. You get the idea, right? So change the frequency word. You change the frequency word, and we can change the frequency. And that's basically how you would control that. Now, you'd have to write your code or set your frequency registers however you want. I'm also going to, so I'm going to take the, so we talked about doing the hardware resets. I'm going to take the reset pin now, and I'm just going to put it to, so right now I've got the pin pulled, and you can see it's kind of bouncing. Of course, it's because it's not being held in any logic state, so it's going to bounce back and forth. But we'll set, I'm going to plug it into the 5 volts, and now we see, so like I said, when we take the reset pin high, we get an output of mid-scale, which is what the data sheet says we will get. And all I've done is taken the wire, the yellow wire from the reset pin, and connected it to the 5 volts, which is going into the Arduino board to give it a logic high. We take the logic low. I'm going to plug it into the ground, and now the logic's taken low and the part is taken out of reset. So we've done that without writing to the code, which is what we wanted to do, or what I wanted to do for this. Alright, so that was pretty interesting and all, but now let's look at the actual project I'm working on. This is the project I actually have set up right now on the breadboard. As we can see, I've left the Arduino board when I'm doing these sorts of projects I like to I find I like to work with the Bear microcontroller. It's still running the Arduino bootloader or whatnot, but I have it set up on a breadboard here because I'm not going to put an Arduino board in a project I'm building, so I'm going to use the actual chip. But what I've got here on the board is a AT9834 chip here, and it's just set up with it's got a 16 megahertz crystal. I've got this button here is a reset. I've got an LED there to give me some status indications. And I've got my SPI commands buses set up here, these brown leads, and I'm using I'm no longer using the AD9834 on the breakout on the little the boards, the little setup boards. I've got them. I've got some more. These are also AD9834s that I just bought in chip form, and I've got them attached to breakout boards so that I can use them on my breadboard. And that's what I've got set up here. Of course, when you do this, you don't get all of the, you don't get all of the extra attachments like the clock oscillator, or you also don't get these nice output filters here. So what I've got, I've had to go and set up my own clock, which is here. So this is I think this is a 10 megahertz. So I've got these running at 10 megahertz now. This is a 10 megahertz oscillator chip, and I've got the ancillary components here set up for these AD9834s. Just real quickly. Otherwise, here I've got two buttons here. These are controlling functions for my project that I'm working on. This chip here is a CD4093. It's just used to debounce the switches, debounce in hardware, because I don't want to fool with writing a software debounce function, so I just debounce in hardware. I've got two relays that I'm going to use to turn the outputs of these devices on and off. And I've got this is an op-amp circuit here, which is just set up as a peak detector so that I can feed a level back from the pilot back to the microcontroller. As we can see, I'm measuring the pilot level here on our microcontroller. And we can see right now it's showing pilot on and a level of 0.76 volts. And then I'm communicating with I've got a USB to serial interface that I'm communicating with the microcontroller through to send the code over from the computer to the microcontroller. All right, and we can see on the oscilloscope here, now I've got, I'll change this over to measure the frequency. So we'll look at the frequency on, let's see, look at the frequency on channel 1. All right, and real quick, the setup, I've got channel 1 looking at the 19 kilohertz output, which is right here, which is going to be the first chip. The second chip's producing a output of 38 kilohertz, and the channel 3 is looking at the output of the clock. As we can see right here, so we've got channel 1 showing 19 kilohertz, channel 2 is the 38 kilohertz, and channel 3 is the clock there. And as we can see, now when you don't use the boards, like I mentioned, when you don't use these boards, which have these nice output filters on it, you get a lot of noise. You get some noise coming out from, it's basically just clock noise that comes out on these outputs. And when I put this in a final form, I'll have to include an output filter to filter out the clock noise. But what I've done on the oscilloscope, I just set the bandwidth filter to 20 megahertz on the oscilloscope, and that does a pretty good job of cleaning up this output signal here to get rid of some of that clock noise. And we can see there that we've got pretty good, pretty clean output there on the 3819 kilohertz. All right, we'll take a look at the code now and see what we're actually doing in this project. We're going to include the SPI library. We're going to include the wire library because I'm writing to a I2C LCD display, which is this liquid crystal I2C. We're going to use that library as well. We've got our pins. We got our LED. We talked about that. We've got our two. Since now we're controlling two AD9834 devices, we've got to have two separate chip select pins, or two separate F-Sync pins, which is that's one of the drawbacks to using the SPI protocol as opposed to using like I2C or something. It's not addressable, it's chip select addressable. So for each device you want to operate, you have to have a dedicated pin to enable that device, and that's what we've got set up here. We've got one reset pin, which I have wired to both of the reset pins on both AD9834. So essentially, when the reset pin is activated by the microcontroller, it places both chips simultaneously in a reset condition, and when it goes to release the reset, both chips will release at the same time from the reset state. And if you read the data sheet, it talks about latency in the output of the AD9834. There's a clock latency where the clock has to essentially clock the data through to produce an output. And again, the reason why I wanted to use this chip is because I wanted to be able to control those resets in hardware, meaning I wanted to be able to place both parts in reset or both parts in enable at the same time, as opposed to doing them sequentially. And since they're both parts are being clocked off of the same clock source, the program will execute in the same sequence. We've got two buttons here. That was our yellow and our green buttons there to control the relays, which will ultimately be used to remove or supply the pilot tones, either the 19 or the 30 kilohertz pilot tones. Those are our buttons, and I've got our relays, which again using to control the pilot tones. And then we're taking one analog input for the pilot level sense. We've got some more integers there, things to control the programming. We've got flags for our buttons and our pilot status. We'll set up our LCD. We're using a 16 by 2 line, 16 character by 2 line LCD. All right. Anyway, so pin modes, and we're going to set our reset. We're going to write our reset control high like we did before. Write our LED low, and then write our F-Syncs, both of our chip select pins high, because they have to start high and be taken low when we initiate a command. Initialize the backup again, or rather we'll initialize our LCD, we'll initialize our SPI mode 2 like we talked about in the previous section. And then I've got some stuff that is going to show on the LCD display. When we first start up, we'll put a message on the LCD initializing, and again we're going to run through our 3 routines just like we did before, this time a little bit different. Alright, so the first thing we're going to do is we're going to run to our reset routine, which is going to place both AD9834s into a software reset, where we're using the software to control the reset, which is right here. We'll place both of our AD9834s in reset, and we'll do that. We'll place the first one in reset, place the second one in reset. Now, at this point, both of our AD9834s will be in reset. Once that's complete, we'll go to our frequency routine, which we're going to now set the frequency for both of our AD9834s. We'll write to the first AD9834 here, and we will install our word for 19 kilohertz. In this case, because like I said, we're not using the same clock frequency anymore, so you have to recalculate your frequency word. And for a 10 megahertz clock, our frequency word is going to be a hex 484B and a hex 401F. And that's the word that we clocked in for our 19 kilohertz frequency. We're going to set the phase of our 19 kilohertz tone to 0, which is what we've done here on our phase register. And we're going to write our F-Sync, our chip select, for the first one high to let the chip know we completed the data transfer. Alright, now we're going to set up our second AD9834, and for this one we want to generate a 38 kilohertz tone, and for again 10 megahertz we've got our frequency word is calculated at hex 5096 and a hex 403E. and that's our frequency word. And we're going to shift the phase of our second AD9834 so that we can align the phase with the 19 kilohertz pilot tone. And in order to shift the phase, we're going to use the hex word C4 to F. And that word is, I came up with that word based on essentially trial and error, doing some rough phase difference calculations. That was the word that got the phase aligned with the 19 kilohertz pilot tone when accounting for the latency and whatnot in the circuit. And so we're going to write our frequency word, and then we'll write our phase word to the phase register. I believe it goes to phase register 0 of the second AD9834. And we're going to terminate the transmission by setting the second chip select pin high here. All right, and so now we've set our frequency, and now we're going to enable our AD9834 chips. And just like we did before, we're going to enable them in a hardware reset condition, where we enable the pin switch pin and leave the reset pin with a reset high, so that the parts exit the software reset into a hardware reset condition, which is what we do in our enable. At this point, we're going to write to both chips sequentially, and the way I do that was I just wrote both chip selects low. That tells both of them to receive a command. They both receive the enable command, and then they both go high to terminate the transmission. And like I said, they're both of the AD9834s are left in a reset condition, and that is because our reset pin, which was right here, was set to high when we started the program, so it was going to be left in a high condition. All right, we got a software delay here, 2 seconds. We're going to display a message on the LCD, which is initialization complete. We've got a 1 second delay, and now we're going to turn on our relays. This will apply the 19 kilohertz and the 38 kilohertz signals through the relays to the analog matrix, which does all of the mixing for the left and right channels. Pilot flag and the carrier flag are going to be used to display messages on the LCD display, and we're going to set our button flags here to set up our buttons for toggling the relays on and off. Clear the LCD and set this number here to integer 10, which I'll explain in a minute. Once we've done all of those things, we're going to digital write the reset pin low, which will take the AD9834s both out of reset, and that's what gives us our... So we've taken both of our pins out of reset, and we can see that we've got our 19 kilohertz and our 38 kilohertz tones being generated here. And they're both starting at the same point. So the 19 and the 38 kilohertz both start at the same phase. Our 19 kilohertz completes one complete cycle in the time it takes our 38 kilohertz to complete 2 complete cycles. They both end at the same point, or they began at the same point. The next part of the code is another routine I've written to update the LCD, and all I've done is I'm using a switch case to basically change the message on the LCD display. Case 10 is going to tell us the pilot's on, and set the pilot to the V for voltage indication there on the pilot tone. And at each time when the case is complete, it's going to change the value of val, and that explains why up here we set val equals 10, which will put us into the case 10, which is going to display this message here. We set it to 0, that's going to exit the switch case. So otherwise, what happens is if you don't exit this, it runs continuously and it makes the LCD display flicker, which is not very good. So we'll write to our LCD, we'll exit the switch case for 0, If there's no zero, it's going to just exit the switch case and not run any of these updates. All right, so back down into, and I guess I should have talked about this first, but this is our the main loop of our program. At the top, we update the LCD, and we write our digital, our LED pin high, which just is an indicator for me that the program has completed writing to the AD9834s. And next thing we do is we look for a button change on button 1 or button 2, and we look for our pilot flag to change, and we have a 100 millisecond programming delay, and then the program runs over and over again. Alright, so we'll talk about what each of these functions do. So we update the LCD. We're going to look at our buttons. If our button changes state, it will change the state of our pilot flag. It's going to turn the relay either on or off, and it's going to send us to, so if the pilot flag is low, meaning that we turn the pilot tone off, we'll go into case 11, which is going to write pilot off on the display and write 0 volts for the level. And then we'll reset valve back to 0, exit the switch case. If button 2 is depressed, which is for the carrier tone, and again it will reset the carrier flag. We're going to write our carrier relay to low, and we'll go set valve to 12, which is going to send us to case 12, and we'll set a carrier off message on the second line of the LCD. If our carrier flag is high, we're going to set valve 13, which will clear the LCD. All that does is clear the LCD and sets it up for showing us the pilot again, which is going to go to case 11. We'll write this information again to the pilot, or to the LCD, and we'll set valve to 0 and exit the switch case. We've got a if for the pilot flag being high. So if the pilot flag is high, this is going to tell the microcontroller to take a reading on the pilot level and display that on the LCD. We'll use an integer for V for the analog read on the level. That's coming off of the peak detector circuit, which we looked at on the breadboard. We'll set float Y, calculate our voltage, and we will display that voltage on the LCD starting at position 11. And that will be displayed on the LCD continuously because nothing is updating any of the other characters on the LCD at this time. And that's essentially how that works. That's where I've gotten so far with this project. I've also got the analog matrix set up. We'll look at that probably in another video, because I think this one's running kind of long. But one more thing we'll do before we end this video is we'll just run through a demonstration on the of the actual controller running through the different displays. So we can see here our display. For some of the moves, I'm going to go ahead and reset it. We'll show what the display does here on a reset. So we're initializing, and then complete, pilot's on, 0.76 volts. So if we press the green button, I think is the pilot one. We'll press the green button. That's going to turn our pilot off, and we're showing 0 volts. And all that's doing now is just essentially turning the relay on and off. I don't have these signals actually going through the relays. But anyway, that's ultimately what's going to happen is the pilot and the 19 and 30 kilohertz signals will be fed through these relays on into the matrix circuit. So we can turn the pilot on and off using the green button. So pilot on and pilot off. And our other one will turn on the carrier. When we do that, we get a carrier off on the second line. We can turn the pilot off too. We can turn the carrier off. When the carrier off, when the carrier is turned back on, then the carrier off message disappears. And the reason I have that set up is because the only reason I would want to turn the carrier on and off is when I'm, if you're doing an alignment on the matrix, on the mixer matrix portion. I don't plan on being able to turn the carrier on and off from the front panel. So I'm just going to have that carrier off there, sort of like a, I guess like a maintenance message for this. But anyway, you know, it can be changed. That's easy enough to change if I decide later on to do that. And then one more thing we'll look at is we'll just vary the level here so that we can see that as we adjust the level going in, our pilot level is going to change, and that's going to I had this set so that when it was set to about 0.47 volts or so, that corresponds to the actual peak voltage. So this is essentially a calibration point here for the level on our LCD display. But and again, what I intend to do is have the peak detector sample the output, the pilot tone output, because I'm going to have the pilot tone actually wired to an external BNC connector, and then this peak detector will sample the output on the BNC, so downstream of the pilot level control, so that will actually give us a real-time indication of pilot levels, so that when we're setting the pilot level to set up our composite signal, we have an indication there on the LCD of what the pilot level is. So we talked about using the phase shift function on the in the phase register, and I'm going to show that here because now that I've got two of these AD9834s hooked up and running sequentially, we can actually see a phase shift. It'd be kind of hard to see a phase shift of just one signal. So what I'm going to do is I'm going to change the phase shift register of the 38 kilohertz tone. And so we see on the oscilloscope right now, this is the with both of the 19 and 30 kilohertz tones in phase, with the word, the phase word from the program, which was C4 2F. And what I'm going to do is I'm going to set this to be C000, because as you remember, when we put that word C000 it should give us a phase shift of 0, or no phase shift essentially. And we'll look at, and what I'm going to do is I'm going to go ahead and flash this code to the micro now. So it's going to go through a little bit of reset here. All right, and there is our output. So now we can see that we shifted the phase of our 38 kilohertz tone, which is this blue tone right here. So they're no longer beginning at the signals are no longer beginning and ending at the same point. When the 19 kilohertz tone is at the bottom of its travel, the 38 kilohertz tone is still coming down and bottoms. By the time it bottoms, the 19 kilohertz tone has already started back up again. So they're no longer starting and ending at the same point here with our two signals. Now, if we set, I'm going to set that. I'm going to set that word back to the shift word, which I had was C4 2F. I'm going to set that back. So we've got that phase shift word set back to C4 2F, and I'm going to go ahead and flash that to the micro here. And there we go. So now we've shifted our tone back in tone. So now they're both starting and ending at the same point. But anyway, so that's just a sort of a demonstration of using the phase, writing to the phase register. Now, one thing we didn't talk about on this in this video was, there's a whole lot of other functions with these chips. And the control word here tells you all of the functions you can write to. You can put various portions of the chip in sleep. You can change the output to put out, if you don't want a sine wave, you could produce a square wave, or you can use triangle waves. And the way it does that is there's a where is it? The sine ROM. If you bypass the sine ROM, or essentially you put it to sleep, which turns it off, then you can produce, I believe, triangle waves. And if you use the comparator, that's used to produce square waves. And all that's talked about in the data sheet. And I'm not going to go into the details of that, mainly because I haven't really fooled with it. Although I'm sure, talking to the part, the way that I've done in this program, you would address it the same way, and you would have to use these control bits to set up those various functions, whether you wanted to bypass the sine ROM, whether you wanted to use the comparator, produce square waves. All that will be done using this the control word here and talking to the control register. And like I said, it talks about it in the data sheet, and you can pull the data sheet up and play with it all to your heart's content. This is more or less just talking about some of the things that I've learned using this part to put it into a project that I'm building. And I hope some of the information here has been helpful. Again, my disclaimer, I am certainly not an avid coder by any means, and I'm sure there are things that could have been done more efficiently in my code. And there are probably instances where I've used the wrong terminology, byte, or whatever. But anyway, that's my disclaimer, and this is the information I have. Hopefully, my next video I will have some more off of the breadboard onto a more permanent assembly. To show you project update. If you would like to see more information on this project, you can look for the next video, because that's what should be coming out next. And that's it for this video. If you like the video, give it a thumbs up. Subscribe to the channel if you like the content. I'll continue to try to put up more content as my personal life allows. And until then, we will see you next time. Thanks for watching.